So I'm going to be studying a very different system, a very different problem than Bob was talking to you about. But this is some results of research that my students and staff and I have been doing over the last couple of years. And as you will see, there's a lot of contributors from outside of USF in this as well, from as far away as Australia, actually. And I'm looking at various different aspects of the dynamics of the Southern Ocean using lots of data sets, not just observations, but also in situ observations as well. And I apologize, I have quite a few results, so I'm kind of giving you the highlights of it and not all the details. I figured most of you aren't really interested in the details, you just want the highlights. But if you are interested, most of these are either published in press or in review, so if you have questions, I'd be happy to share the preprints or reprints with you. So first of all, let's talk about what we know about the dynamics of the Southern Ocean and the circulation in the Southern Ocean in 2 slides. You know, it's going to be a very, very brief overview. So you've probably heard of the Antarctic circumpolar current, right? It's not a single current system, though. It's actually comprised of several jets and then very low circulation between these jets. And it's often categorized as 4 major front systems: the South Antarctic circumpolar current front, the polar front, the subantarctic front, and the subtropical front. One thing to note here is that the subtropical front actually doesn't pass through the Drake Passage, and that explains the return flow through the Indonesian through flow. It's about 10 spheredrips of mean flow into the Pacific that doesn't leave the Pacific through the Drake Passage, that has to go through the Indonesian through flow. But it's very variable here in the Indian Ocean, and so we need to account for that. The dynamics are set up by not only the winds, although the winds tend to set up the mean circulation, but also the buoyancy forcing, basically the precipitation, water exchange, and the heat fluxes as well. I don't really comment on those here, but this is just the map of the mean zonal winds from satellite data from 1992 to 2010, and you know, these are the roaring 40s in the southern hemisphere. And it's also, of course, set up by the fact that there is no eastern boundary in the Drake Passage. And so that means that the forces on the surface have to be balanced by basically drag at the bottom. And so that allows the current to go all the way to the bottom, unlike most other current systems in the world. And here's just a demonstration of that from a review paper by Cunningham et al. In 2003, showing integrated transport from CTD cast on various cruises in 96, 97, 2000. And so this is integrated, assuming zero velocity at the farthest southern extreme, and then integrating the velocity vertically and south to north as well. There's a couple of differences between these lines, and I want to point those out because it's very important to why we need to take measurements of the current system. The solid line here is assuming that at the common level, which is about 2,500 meters depth in these transects, that there is no velocity at that depth, okay, that there's a zero velocity. With the CTD cast and looking at gradients of the density at various pressure levels, you can only get the relative geostrophic shear, the relative current. You cannot get the absolute current from that measurement. And so you have to have a reference. And so typically, it's assumed to be 0. Okay? But here's actually a measurement of the velocity at that 2,500 meter depth, and actually in some places a little bit lower, from a lowered acoustic Doppler current profiler. And you can see here is that you can have variations in the velocity as much as 20 centimeters per second. Okay? And ignoring that 20 centimeter per second bias in your reference velocity integrated over that entire depth of 3,000 meters or so is a huge change in the transport. So for example, if you look at the solid line, in all cases, it's right around 125 to 130 spheredrips for the total transport. But if you include that bottom velocity, it can either be a lot less or a lot more. So knowing what that velocity is at depth really contributes to the variability of the transport, of the integrated transport of the ACC. And that's something that we would like to measure, and it's very difficult to do using a ship-based measurements in only a few locations at a few periods of time over the year. And so there's been a lot of effort to use either satellite measurements, autonomous in situ measurements, and data assimilating models to understand this problem. And so I'm going to focus mainly on the observations. All right, so how do we get that reference velocity at depth? Well, one way to do it would be to have autonomous vehicles, and it'd be nice if they could actually have acoustic Doppler profilers autonomously throughout the world's ocean, but those are kind of expensive, and that system has not been developed yet. But instead we have the Argo system, which measures temperature and salinity as this float rises from depth to the surface. It'll stay there for a few hours as it reports the measurements, and then it sinks back down to 1,000 meters depth, 1,000 decibars pressure level, and then it drifts for approximately 9 days. And then it repeats the cycle again. Well, if we can get a fix at the surface when it was between that 9 to 10 day period, then we can actually infer what the drift was at depth. There's a lot of problems with that. First of all, you have to get a correct fix with GPS that's reasonably good in most places, except when you have very high waves, you get what's called aliasing effects, because the high waves will reflect the signals differently. A lot of the Argo floats actually don't have GPS on them. They rely on a radio Doppler effect to fix the position. And so there's errors in fixing the position. And moreover, in the Southern Ocean, you have lots of mesoscale eddy variability. And so sometimes, if the main current is going this way, an eddy can transfer it this way. And so those in the editing are often removed because it's not reflective of the actual drift of the currents at depth, because the eddies are intensified at the surface. So there's a lot of editing of this data that happens, and much more so than the actual temperature and salinity data that we get from the profiles. And if you actually look at the amount of observations that are available to study for this velocity at depth, you actually do not have a whole lot over a 5-year period. So this is the amount of observations within 3 months period in 2006, and you can see at the most you may have 3 velocity measurements over that 3-month period. If you extend it to a 5-year period, you can see you have more observations up here, a lot fewer observations down here, maybe on the order of 10 to 15 observations over a 5-year period of velocity at 1,000 decibars. And this is actually the area where we're most interested in, because this is where the velocities in the Southern Ocean are the strongest and where we want to get that information. Up here, the velocities are almost 0 at depth, so it doesn't really matter if we have 100 observations of that velocity at depth. It really doesn't really help us that much. What we really want are velocity measurements down here. And again, I just want to point out that all of the slides I'm showing for this first section is from this paper from Mike Kasimpa and I that we published in JGR over the summer. And so there's another way that we could do this, and it was actually proposed about 30 years ago by Carl Wunsch and Kapashkin, so an oceanographer and a geodesist. And it combines 2 different data sets. There are certain assumptions in this, and I think we're now at the level that we can start to use this. And so the first one is that if we have the sea surface height measured by a radar altimeter in space, and we have a gravity field also measured by satellite observations to give us the mean geoid, we can differentiate that absolute dynamic topography, and we can get the surface geostrophic currents at the surface with no bias. Again, that's assuming that there's no bias in this measurement right here. Now, the traditional method, and what was used in the Cunningham et al. Paper, is essentially this one, where you're looking at the density from temperature and salinity integrated up from pressure levels and taking the derivative of that. That is going to be biased by this unknown reference level. And so in most regions of the ocean, assuming that it's zero at some great depth is okay. But here's just an example of 1 month from this dynamic topography calculation. So this is from the Argo to 1,000 meters depth. This is from a altimetry minus a high-resolution modern geoid from satellite gravity data and surface gravity data. And you can see this large difference here in the Southern Ocean, right? That is indicative of a strong current at depth at 1,000 decibars, or an error in this measurement, one or the other. What I will argue and show is that it's really indicative of a large current at that system. And so if we have these two independent measurements, and they're biased by this reference current, we can actually just difference them and estimate what that current is at depth, that geostrophic current at depth. And so again, this was proposed 30 years ago, and it has only recently been able to be verified and used, because now we have global measurements of this from the Argo array, or near global measurements. We also have global measurements of this that are not biased by gravity errors or sea surface height errors significantly. All right, and so this is a 5-year estimate of the mean geostrophic currents from this method at 1,000 meters depth, the top, and then the bottom is the same one estimated from the Argo drift that I showed you previously. Qualitatively, they look very similar. You see the currents of about the same magnitude in the same locations, intensification near seamounts. The correlation is high. The standard deviation is within the expected errors. But we can actually start to look now at the temporal evolution of this as well and compare the data sets and do more formal statistics. And so if we look at 3-month 5-degree average currents from the Argo drift and this combination that we've done over the 5-year period, we can compute the standard deviation, and that gives us an estimate of the uncertainty in our current estimate. Now, one thing we have to take into account, though, is that this drift estimate is not perfect. It does not have zero error. In fact, the uncertainty estimated with it is about 3 centimeters per second. Actually, higher errors where there's higher currents because of the eddy variability. And in fact, the mean standard deviation over this time period from our method and the Argo drift method is about 3.9 centimeters per second. And so if you go through the math and assume that the uncertainties are uncorrelated, you can actually show that the uncertainty in this method is actually lower than what's estimated with the Argo drift method. Moreover, you can see that in some locations, the differences are very, very small. Basically, where the currents are small, the uncertainty is small. Where the currents are high, like around here, the differences are higher. And from all the testing that we've been able to do, we believe that this is more a problem in the Argo drift than in our estimates, mainly this contamination from the mesoscale eddies. And here's just a highlight of that to show a time series to emphasize something else. These trajectory measurements, based on the drift of the Argo, you only have a few samples over this time period. Whereas the method that we use, based on the gridded altimetry and the gridded temperature, salinity, density fields from Argo, we can get an estimate almost every month. Okay? And so they agree fairly well, except for a couple of outliers. And these outliers are more than not likely due to eddy contamination from the drift in the Argo floats. Moreover, we have many more observations of this surface current that we can utilize in calculations of transport. And so we can put that all together now that we have a better estimate of the current at depth as a reference. We have the density profile from the Argo floats. We can compute the total geostrophic currents from some reference level, integrate it up, and get transport across a section of the Southern Ocean. And it's very revealing. So first of all, I want to point out this green curve. That is the transport estimated from the Argo data alone, basically the density measurements, if we did not have a measurement of the reference current. And basically, if we assume the reference current was 0. You can see what happens when we actually include the reference current in there. The transport increases. But the other thing to note here is the red is the one based on the combination of the surface currents from altimetry and the Argo density gradients. And the blue uses the reference current from the Argo drift. So there's some significant differences between them. First of all, the variability from one longitude to the next is much greater in this one. And that is not realistic because momentum should be conserved. Okay? If we go from all the way to Antarctica, all the way to the tip of some boundary, it should be conserved. Now, one issue here is that we do not have data below 60 degrees south. That's a combination of the altimeter ground track and the fact that there are no Argo measurements in that region. And so this does not conserve the momentum as much as our estimate from the Argo and JSON data do. They agree momentum balance within the uncertainties that we estimate. Moreover, this one is biased significantly higher than the expected transport measured by other very precise measurements at the tip of Africa, which is about 150 spheredrips a mean. It's biased high by about 35 to 50 spheredrips. And all indications that we've been able to test is that this drift estimate is biased a little bit high from the Argo drift, much higher than what we get from our method. All right. And so from this now, we can actually start to look at transport variability in the Southern Ocean along various sectors and start to look for changes in the transport and relationships and types of variability in the transport. I'm not going to detail that too much here, but the only comment I'm going to make here is this is still only down to 2,000 meters depth because that's the lowest level of the Argo array. We cannot do it deeper. Okay? Changes in the currents below 2,000 meters are still unobservable with this method. And as we showed earlier, those can have a significant contribution to the actual total variability. Okay? So I'm going to take a small detour now to do another little project that I was working on, and that's looking at the eddy kinetic energy versus transport in the Southern Ocean. And this arises from several modeling studies that have been conducted over the last decade or so. Okay? So climate models get the large-scale variability of the ocean reasonably well, but they do not capture the mesoscale energy in the ocean. To do that, you need very, very high-resolution models, which are very computationally expensive, and they're usually limited to small regions, small periods of time. And if they want to do a very, very long run of these high-resolution eddy-resolving models, they have to make some simplifications, basically in the bathymetry, the land, ocean areas, things like that. They use fairly constant winds, things like that. But these two different types of models have shown very different things about how the transport and the eddy kinetic energy in the Southern Ocean evolves with a change in winds. So they both tend to agree on interannual time periods, showing that there's an acceleration-deceleration in the transport of the Southern Ocean related to variable winds. But on longer time scales, this is decadal to century, they disagree considerably. These coarse climate models suggest that as the winds increase, the transport will increase as well. But the high-resolution mesoscale eddy models suggest the opposite. They suggest that the transport does not change significantly, but the eddy kinetic energy, i.e. more mesoscale eddies are created, they're more energetic, and they contain all the energy put into the ocean from that increasing wind. And so these models suggest these two different things, and so we've been trying to look at observations to see if we can differentiate. Is the eddy kinetic energy increasing? Is the transport increasing? Because we do know that over the last 20 years or so, the southern ocean winds have been slightly increasing over time. So it's common to look at this southern annular mode or Antarctic Oscillation index as an indicator of the change in southern winds, because that's the leading mode of the southern winds. And this is just to show some of the interannual variability in the winds in the southern hemisphere, the trend from the 70s on. There's kind of a quasi-biennial type of period. There's a large peak in 1997 related to the INSO variability. And I want to point out that this is a paper that we have just been accepted in press. I want to point out that this whole work that I started doing here derived from a conversation with Mike Meredith when he came for the Eminent Scholar Lecture 2 years ago, and we were sitting at dinner talking about our mutual interests. And he had written a paper with Andy Hogue a few years earlier looking at eddy kinetic energy and said that he didn't think that there was any change in eddy kinetic energy. And I said, well, you were using gridded data and that attenuates the signal. I think if I go back and look at it with crossover data, which gets the higher resolution velocity fields in the Southern Ocean, but only at discrete points, that we can actually find that it may have increased. And so we started talking about that and playing around with it. And we actually found what I suspected, is that the gridded data attenuated the signal in the eddy kinetic energy, and using the higher resolution crossover data from altimetry that's available, we could actually see that the eddy kinetic energy had increased over the last 2 decades. And it's significant. It's about 15 to 20 centimeters per second squared per decade. And if you compare it relative to the relative eddy kinetic energy, it's